and welcome to A Ramble with me. Today we are rambling about the May 2022, paper 2 from the department, question 5.3. Given the identity sine 3x divided by 1 minus cos 3x is equal to 1 plus cos 3x divided by sine 3x, the first part of the question asks us to prove this identity. I've seen an identity that looks like this except without the threes. So I think I kind of know what to do. Um, so, I mean, yeah, at first it looks a bit weird because it looks like we're flipping the fraction around, but here it's a minus and there it's a plus. So the trick here is we need to multiply the bottom by the conjugate. So instead of 1 minus cos 3x, we times it by 1 plus cos 3x in order to create a difference of two squares, which will then result in some or other, I forgot what. I think we end up using the squares identity anyway, but it ends up working out. And I am fully aware that I'm using a cheat code, but maybe that is something to uh, add to your library of possible approaches with identities. But yeah, the giveaway in this case is that you go from having a 1 minus cos 3x in the denominator on one side to having a 1 plus cos 3x at the top on the other side. So yeah, you're going to times top and bottom by this guy in order to make him appear at the top. But here at the bottom, it's going to end up actually being a sign. You'll see. Trust me. What's my proof? My proof is trust me, bro, as the kids say. Right. So we have sine 3x. This is what's happening on the left-hand side. Yeah, this is one of those identities where it doesn't really matter which side you start with because I think they're equally, they're at an equal level of difficulty. So we're timesing top and bottom by the conjugate so that we create a difference of squares down here. Do you see what the difference of squares is going to be? It's going to be 1 minus cos squared 3x. And we know that sine squared 3x plus cos squared 3x would be equal to 1. So that's what we're trying to go for there. So up here, I'm just going to keep it as sine 3x times 1 plus cos 3x. I'm not going to multiply it in because I can see that I end up with a 1 plus cos 3x on this side. So even if I multiply it in, I'm probably going to have to end up factorizing anyway, or yeah, doing some cancelling. So it is not not right. So that's the difference of squares we end up with. And that, my friends, at the bottom is sine squared 3x, right? This is coming from the fact that sine squared a plus cos squared a is equal to 1, right? So if you move things around, you're going to end up with sine squared a is the same as 1 minus cos squared a. And in this case, our a is simply 3x. Okay, 1 minus cos squared 3x is the same as sine squared 3x. Nice. So that's what I was very clumsily trying to describe at the beginning of this video. Anyway, I hope it makes sense now. So we can now cancel this sine 3x with one of the sine 3x's here. Remember, this is sine 3x times sine 3x. That's what that square means. So this is just the same as 1 plus cos 3x divided by sine 3x, which is the same as the right hand side. Yay, we did it. We did the thing. So our identity is officially proven. Now, next part of the question. Given that same identity, Determine the values of x in the interval. X is an element. How do we even read this? So for the values of x between 0 and 60, including both 0 and 60, we want the values for which the identity will be undefined. So in this case, cos and sine themselves do not have any restrictions on their domain, as in you can input any real number for x and sine and cos will be defined, unlike tan, right? So we're clear on that front. So the only thing that's going to cause this identity to be undefined is if we divide, if any of the fractions involve a division by zero. In other words, it will be undefined if 1 minus cos 3x is equal to 0, or if sine 3x is equal to 0. So these are then two equations that we need to solve. We're first going to get the general solution, and then we'll get the solutions that are in this interval that has been specified from 0 to 60. So this is the same as 1 is equal to cos 3x. And we know that our cos graph, oh, sorry, pain in the side, in the oblique. Right, so we know that cos of A is equal to 1 when A is 0. So just need the visual real quick. So it's going to be over here that we're equal to 1, and then again a period later at 360. So, okay, maybe I shouldn't write that. Okay, so that means 3x is equal to any multiple of 360, right? Because it's 0, 360, 720, and so on, negative 360, and so on and so on. So then we can divide both sides by 3. So that becomes x is equal to k 120. And k is an integer. I'll put that in when we have our second solution. Next one is sine 3x is equal to 0. So if I just draw one sine wave, that is happening here and here and here and so on. So 0, 180, 360. So this tells me that 3x is equal to 180 degrees, any multiple of 180. So we then divide by 3, and that becomes x is equal to k times 60, right? And these are then our two solutions. And maybe some of you are wondering, for my these two little graphs that I drew, why did I draw the graph of y is equal to cos x and y is equal to sine x instead of the graphs of y is equal to cos 3x and y is equal to sine 3x? It's up to you how you want to interpret it, right? So all I've done is, maybe it will become clearer if I don't use x as my variable in my function. But this for me is the same as, okay, the graph of y is equal to cos A and the graph of y is equal to sine A. So I've found the angles A, which is in this case 0, 360, 720, and so on, that will make this equation true. And now I go a step further to say, well, okay, but my angle is not just A, it's actually 3x. So now I equate the 3x to the A and I solve for the x. So it's kind of a double solving. Whereas maybe if you wanted to sketch directly, so if you wanted to sketch y is equal to cos 3x, so that would be a cos graph whose period has been shrunken by a factor of 3. So instead of going from 0 to 360, one period, it'll go from 0 to 120. This will be 120. So, and then it'll go again until 240 would be the next time the period ends. And so it goes. So then your solution would be that um, x, so sorry, y is equal to 1 when x is equal to 120 or 0 or 240, etc. Right? Or in other words, um, x is equal to k120, where k is some integer. And that is what we do indeed have as our answer there. So it doesn't really matter how you arrive at it. Um, so this is pretty much at this point, we're kind of taking this graph and shrinking its period, right, by doing that division by 3. So yeah, maths is your oyster. That's the beauty. So now let's not forget, we're trying to find solutions in a specific interval. So we're looking for solutions in the interval 0 to 60, inclusive. 0 and 60 are both included. So with this solution, um, we're going to have, if you do k minus 1 times 120, you're going to have minus 120, which is too small, 0 times 120, which is 0, and then 1 times 120, which is too big. And so anything bigger will also be too big, and anything smaller will be too small. So 0 is the only solution that we can take from this solution. And that's because the 0 is included here. So it's very important to know what those brackets mean. And then from this solution here, if we start with -1 for our k, we have -60, which is too small. So anything smaller will be too small. And then 0 times 60 is 0, 1 times 60 is 60, 2 times 60 is 120. So now that's too big for our interval. So these are the only two solutions that we can take that will fit in this interval. And because, again, the 60 is included in the interval, so this guy can come in as well. So our two solutions are that if x is 0 or if x is 60 degrees, the identity will be undefined. And we can double check that. So if we just calculate sine of 3 times 0 divided by 1 minus cos of 3 times 0, we end up with indeterminate. And let's do 60 on the other side for fun. So we have, oops, 1 plus cos of 3 times 60 divided by sine of 3 times 60, and that also ends up being indeterminate. So that's looking promising. Let's see what the memo thinks of our promises. Right, so for the proof, we have done the same thing. That's fantastic. Love to see it. Love it for us. So an interesting approach that they have, which is related to what we ended up doing with our proof, but they times by sine 3x top and bottom, okay, in order to make this top term a square. And then they rewrote the sine squared 3x as 1 minus cos squared 3x. And then they factorized that difference of squares, which then cancelled out. One of the factors cancels out with this guy. So you kind of end up with the same potato, but it's another way that you could have done it. Instead of multiplying by the conjugate of this guy, top and bottom, you could have just times by sine 3x, sorry, in order to create sine squared 3x, and then create a difference of two squares from that, and then still use this identity to factorize the difference of the two squares and blah blah blah. Anyway, for our final answer, we do get x is equal to 0 or x is equal to 60. So fantastic news for us. Thanks for tuning in, and catch you another time for another ramble.